Hello all mortals. So today we are going to move from propositional logic to predicate logic. So propositional logic is the kind of logic which is concerned with statements such as this: A and B imply C, whereas predicate logic is the kind of logic which is concerned about predicates and how they apply to individuals. So things like this: if X is a man, then X is mortal, and Socrates is a man. And then there's a famous conclusion you can draw from this. So the first thing we have to do if we want to do this in type theory is we have to figure out how we're going to represent predicates in type theory. So what does the predicate say on the natural numbers? And if you think a little bit about this, then we see that things like this: is man X, is mortal X, etc. These are propositions that make sense as soon as you instantiate the X, right? So is man of Socrates is a proposition that talks about Socrates, and is man of X is a proposition which talk about X, if you know what X is. So it makes sense to say that a predicate on some set A is just going to be a function from A into set, because we're using set to represent propositions, right? So I have to give a type signature for this as well. So A is a set, and what we're going to get back is something called a large set, because this thing contains set itself here. So okay, here we go. Here's the typo. Right, so let's look at an example. I'm going to define the predicate isEven, which is going to be a predicate on natural numbers. This makes sense for any A, right? Okay, so that means that I should define a function from the natural numbers into set. And how do I do that? Well, I have to do it like I define any other function. So I write an n on the left hand side, I write a question mark, and I load a file. And then I can pattern match on the n, and I have to give a case for 0 and a case for successor. So since I want this to be the isEven predicate, I'm going to say that 0 is even. So I'm going to say that this is the same as top, which was the unit type which we used to represent things that are obviously true. Right. Okay, what about successor of n? Well, I don't know if this is even or odd yet. So pattern match on the n, and I see that if it's suc of 0, that is 1, then that's definitely not even. So I'm going to map this to the empty type, which we use to represent things that are obviously false. And when it comes to suc of n, well, this is going to be even at exactly the same time as n is even. Right? So I'll just make a recursive call and say that this is the same as isEven of n. Okay, and then we can do some tests and see what happens for concrete things. So let's see if we can prove that 4 is even, for example. Okay, so do this, and then we can see what do we need to prove. We see that in order to prove that 4 is even, we have to give an element of the unit type. Well, we do know an element of the unit type, so that's easy, right? Okay, so why is this? Well, 4 okay, let's just do this by hand. 4 is the same thing as suc of 2. It's going to be relevant in a second, because when we look at this isEven 4, we go through these lines and we see which one matches. And we see that the first one certainly doesn't match, second one doesn't match, but this one matches if you take n to be 2. Right? So we see that isEven of 4 is the same thing as isEven of 2. Okay, and then we do the same thing for 2. 2 is not 0, 2 is not 1, but we do have that 2 is suc of 0. So this last line is going to match, and we see that, right, so what we see is that this was the same as isEven of 2, which in turn is the same thing as isEven of 0, and now the first line matches, right? So this is the same as top. So all we have to do is we have to prove top, which we can do. Okay, so what happens if we try to prove that 5 is even? see what we have to do now. Well, now we have to give an element of the empty type. And why is that? Well, we're going to do the same thing where 5 is suck of 3, etc. But we're now going to end up with this as our base case rather than this. So it's going to compute down to saying, okay, you need to give something of the empty type. So that's clearly not going to be possible. So we should be able to put a negation in front of this. And I can talk about negation because I've imported this relation nullary, by the way. And now we can try to prove this. Okay, so how do we do it? Well, we have to give a function. It looks like we can even do this, but if you want, we could just introduce an x. And then we see that this x here is an element of the empty type. That seems hard. So let's pattern match an x and see what it could possibly be. Well, there are no cases, so we have nothing to do. Okay, so that's one example of a predicate. Let's define another one just for fun. So I'm going to define the predicate of being greater than 1. This again, a predicate on the natural numbers. And I do it just like I did before. So I'm saying it's this. I pattern match on dn. And I say that 0 is not greater than 1, so this is bottom. Suck n, I don't know if it's greater than 1 or not. I have to look at the n. 1 is not greater than 1, so this is bottom. And suck n is definitely greater than 1, no matter what n is, right? Because this is at least 2. And similarly, I can define the predicate smaller than 3, for example, in the same way. So let's do this. Okay, so I say n is smaller than 3, something, and then I pattern match on the n. 0 is smaller than 3, that's true, so I make that \top. Suck n, I don't know if it's smaller than 3, I have to look at the n. Well, 1 is smaller than 3, that's the top. Don't know if this is smaller than 3 yet. This is 2, that's smaller than 3. But this is suck something, so that's at least 3, so this is going to be false. Right. And now if I want, I can combine these different predicates by saying, for example, that 2 is smaller than 3 and 2 is greater than 1. Okay, and then we see what we have to do to prove this. Well, the first thing is computing down to top, and the second thing is computing down to top. So in fact, you can just give an underscore and Agda can figure out what these two inhabitants of top are. Right? Whereas if I change this 2 to be a 5, for example, then I'm going to get yellow here because Agda doesn't know how to find the inhabitant of the empty type, which is fair enough. Okay, so let's change this down to 2 again, 1, whatever you want. Okay, so that's how you represent predicates in Agda.